I will talk about the Slice's Post5G Blueprint, and it's a community work. It's not only my participation. There's a lot of people behind, so I'm presenting today. And this is the outline of the talk. First of all, what is the meaning of a research instrument and how it relates to Slice RI? Then I will focus on the Post5G Blueprint, which is specific aspect of Slice RI. Then I will show a recorded demonstration, a video of 10 minutes. Then I will finish with presenting the current status and some lessons that we've learned from this experience. So first of all, why do we need a research instrument? What is a research instrument? First of all, it's not a test bed because the test bed is considered as too specific, while a research instrument is a broader scope with much longer term vision, allowing for several experimentation types with reproducibility, allowing for some standardization, going to large scale, being sustainable. So all these nice terms and qualifications are interesting for the Slice. And the last one, which is the governance and infrastructure management, are something that's also important. And we were just talking about that before we start, which is people need to engage in funding the research instrument deployment or usage. So why do we need that? Because if you want to do research, many papers nowadays are published by industrial having access to very large infrastructure and doing large monitoring and data collection or testing and validation on a huge number of nodes or systems or whatever. So if you do your small experiment in your lab, you have little chance to compete with those big players. And another aspect is the reproducibility of your results, because some papers have advocated the idea that most published research findings are false because nobody can prove that they are true. And if you try to check something, you will see that it is false. And I talked to you about one paper before that, but I don't want to repeat now the name of the author. So there is a risk and we need to be able to repeat the experiments and to benefit from previous experiments and maybe modify them and enhance them. Okay, so the test bed and platform work is not new for years, whether United States or Europe or Japan or China are strongly involved in mid-scale platforms, which is something going to $200 million or euro, which is very high, very expensive. But still, all these efforts are a bit either too specific or they are short term. That's why in Europe there is a program under the Pillar 1, which is called Research Infrastructure, okay, that can fund scientific instruments going from with the cost can reach up to 1 billion euro, which is huge. Okay, those are examples of what has been funded with S3, which is this European framework funding those. So whether the SQA or the Collider in Switzerland, and then what is needed is therefore a scientific instrument. Like those scientists, those physicists using those equipment to do their research, we need an instrument so that networking and more largely digital sciences people, researchers, do their research with a scientific instrument. And this will help to enhance the results and the reusability of the results. But it means that the infrastructure itself should be adapted to the type of research. So if your testbed is not of interest to me I will not use it. So if we want to put a huge effort to build an infrastructure, it should serve a wide spectrum of researchers, and this should be taken into account in the design of the infrastructure itself. So Slices is the project that were put on the S3 roadmap in 2021, okay? And that will last for more than 20 years, okay, with some regular funding possibilities. Here are the countries that are involved. And yes, there is the Swiss node involved in this project. So there is interest for all these people to contribute and participate to this huge effort. So last administrative slide, which is a timeline of the project. As you might see, the project span until 2042. We are now in 2025. We are really in the implementation and blueprint deployment phase. And then after that, maybe in 2 or 3 years, we will go to operation. It doesn't mean that we will stop all the design and the deployment. Maybe we'll continue in some specific aspect with some continuous upgrade, but it will continue until 2042, which is very long period. That's solving the sustainability, at least for these 2 decades. So now, what is the methodology to design this infrastructure? Well, it's by adopting the blueprint model. And the blueprint is, as I will explain, defined by the researcher community. So you have people working on networking, or maybe on cybersecurity, on internet protocols, all time ago. And then specific research communities can define their domain and the needs of their domain. And this will end up with a blueprint that can be used on the research infrastructure. And in this case, it's the experiments that will be done by those researchers that are the center of interest for the design. So let me remind the blueprint concept. Well, it's a set of definitions and explanations and documents that can help the collaboration between engineers, or maybe two low-level technical people and researchers, and other higher level, broader view people, okay, to develop together some understanding of the needs of the domain. Okay, so there's a terminology so that everybody understand everybody else, even if we don't have the same technical skills or the same broadness of view, so that by the end of the day, if we define this blueprint, we have a clear view of what is required and what are the good resources that should be provided to those people to do their research. And if we want to apply this to 5G, one might ask, but why to choose 5G? Why didn't you do a cloud blueprint? Why didn't you do federated learning blueprint? Well, there is federated learning blueprint. There is a cloud blueprint. But I will talk about the 5G blueprint because I am from the networking domain, and very important, because the key principle of the 5G architecture that will help to define this blueprint are very important. There are all modern aspects of networking, like with SDN, NFV, etc. So all these aspects are put together in the 5G system architecture. And if you define your blueprint to respond to those needs, you will provide a system that will help researchers really do research on future generation networking. So separation of user plane and control plane, having modular function design to allow for network slicing, defining the interaction between functions, as services where you ask for some information and you get the information. You don't have permanent connections between the provider of information and receiver of information to provide more flexibility, while still enabling direct interaction between the functions and the services with the XApp model, where you can get your information without third intermediate node, minimizing the dependencies, allowing for deployment on separate nodes or localities, support stateless network functions where you can decouple storage and compute, and having some nodes that do not have a storage on them, and also exposing capabilities of the network where some provider can use what is available on the network and define a new service and expose this capability to the users. So all these aspects are really interesting to test and to validate and even test the performance and the guarantees that can be obtained, not only in simulation or modeling. We need to go to the experimental part. So that's why those aspects represent the domain that helped to define the 5G blueprint. And then we ended up by doing some deployment of different equipment that can help to have radio access network, to have edge and cloud, to have radio units, to have like even reconfigurable intelligent surfaces deployed on different nodes, different sites with a central hub, and with some private or public clouds that can be helpful to deploy some functions there. So the idea is to provide infrastructure to the users that can be on top of it we can deploy provision some test bed or some research instrument that we want that is adapted to our needs, and then run our experiment on top of it. Okay, so I will go back to this idea. We have a generic equipment. We can deploy and provision an infrastructure on this equipment, and then run our experiment on the equipment. So even the testbed itself, now I call it testbed because now we define what we want, we deploy it, then we run our own experiment on top of it. So the deployment of the testbed is a bit flexible, as I will show here. So what to do? What are the type of research that we can do with this? We can do several types, 5 types here. I will explain them with more detail in 5 slides. But first of all, I would like to emphasize the importance of repeatability, reproducibility, and replicability. And if we don't have this in mind, okay, we still have some results that maybe we can publish in very good conference, but people do not have the possibility to reuse the work to build on top of it. Okay, so one type of experiment that we would like the slices infrastructure to provide, and that were used to define the 5G blueprint, is the vertical service integration and testing, where you need some 5G system, 5G network, but only for the purpose of testing an application. Could be a drone application, could be a robot application, whatever application, but you need some infrastructure. So you don't care about the network itself. It's not your business. What you want is to deploy some software, either in terminals or even in the network infrastructure, but in some cloud or in the RAN, but not to modify the behavior of the network itself. only to test your own application. It's called a vertical service. This is one type. It can involve also adding some hardware if you bring your own device, but it's some specific aspect, okay? And you can also put it in the network, but you don't modify the behavior of the network. The second type of experiment that could be done is SDN experiments, software-defined networking, where you want to modify the behavior of the 5G network itself, okay? So you use, because 5G was designed with those key principles that I mentioned, it is possible to do that. So, but it needs the access to the network functions and to be able to modify the behavior, okay? So you need maybe to deploy some specific controller of the network, etc. This should be possible also. You can also have some specific data processing unit or programmable switch for low-level real-time behavior. So it's like controlling the network and modifying the behavior of the network. The third type, very important one, and for the moment, it's the most advanced in the tests that we are running ourselves. It's doing some experiment with open source software doing 5G. That's why we are mostly interested in 5G. There are open source projects like Open Air Interface or ORAN that have very, very large and dynamic open source communities defining functionalities and testing them. So they can test in their own environments. But if you want, you can test on a very large scale environment. So you can deploy what is existing in this slices infrastructure, okay, and then add your own software on top of it and test your software. You compile your software and you test it on the large scale test bed. Type 4 is having low-level access to radio resources to add some new resources. Okay, this is the most exciting research. Okay, this is like, wow, adding new technologies, reconfigurable intelligent services or terahertz radio. It's not something that is already available now because it requires some specific blueprint. I mean, it requires that people working on, for example, integrated sensing and communication to define their own needs and requirements and to come and add some hardware and software and processes to the testbed, to the infrastructure, sorry, to be able to provide that. So this is, we would like to be able to do so. It doesn't mean that we are able to do so today, but it keeps open, it keeps the slices open to new domains. Last slide, which is very interesting also, it's the joint use of 5G and HPC resources. For example, we want to run a radio network, 5G radio network, but we want also heavy compute resources like GPUs. Why? If you would like to run your 5G network plus a digital twin of your network in the same time, related. Why related? Because maybe you would like to run in the digital twin some large number of terminals that you are not capable of doing in the real network. So you have a real network and you have a copy of this network running in some GPU, and then in this copy of the network you have a large number of terminals that you can launch. Okay, so this is aspect of joint use of 5G and HPC. Another aspect is when we develop type 3 experiments like open air interface Code analysis and bug fixing might require a lot of resources. So GPUs here can help to do this code analysis. Okay, so this is like specific needs that we thought about that to propose experiment that involve both telecommunication and storage and HPC. Now, what is the situation now? Now, concerning the 5G blueprint, allowing for 1, 2, 3 type of experiments, it's already available. Okay, and it's documented, really fully documented, with a reference implementation of this blueprint, which means that we have hardware, we have software that can be configured to run experiments, and it is being used to run experiments today. Okay, everything is automated with Terraform, Ansible, Kubernetes, and the baseline, the reference open source project we use is OpenAir interface, but we can deploy with other than OpenAir interface. But we did a lot of tests with OpenAir interface. And I will show at the end the list of available hardware in the different nodes of slices. So you can have full documentation. I will provide at the end the link. And then you have the gate, and you have some APIs that are available. And then something very interesting, which is called the Slice Academy courses. So in the context of Slice Academy, we have courses explaining how to do things, how to do experiments. And we are doing a lot of video. One of our researchers, Damien Saucez, is doing a lot of demos and presentations of the 5G blueprint. So let me now finish with this slide, then go to the video to present the demo. The main idea of the blueprint is to put the experiment at the center of interest. So first of all, you define your experiment, okay? So we provide an interface to configure your infrastructure. So please have in mind, you have two things. You have the infrastructure to prepare, and you have your own experiment to run on this infrastructure. Okay, so we provide the possibility to configure the infrastructure, to provision the infrastructure, because we provide like bare metal, we provide many things, Kubernetes, and we allow the user to prepare, provision the infrastructure as the demo will show, and then to run his or her own experiment on top of this infrastructure. Okay, and we will see the difference of this, and then we will be able to generate the experimentation code automatically, book the resources, execute the experiment, and then publish the results on a site, on a data registry that will help to get this experiment results later. So this is the interface to configure. This is the interface to book the resources. This is the interface showing the execution of the experiment. And this is the interface showing the publishing of the results. Now, I will stop the slides here and open the video like that to show the experiment. So the experiment itself is a video of 10 minutes, but I will comment it myself. So maybe I will stop the video to be able to talk. So what we have here is a very simple experiment of a ping, okay? Yes, but what is this ping? It's a ping between a telephone, the UE, and the UPF, which is one function of the 5G network, okay? User packet, the UPF. So how do we deploy that? We deploy a 5G core, but not on our local site. We deploy it on a central hub, on a Kubernetes cluster that is on a remote central hub. Okay? So we can, to show that we can run piece of the infrastructure elsewhere than our local node. Our local node being the Sofia node, because we are localized at Sofia. Okay? We have also a machine called a deployment node. Here the name is standard to one, but we don't care about the name. But this machine will do the deployment of the experiment, and it could be local, could be remote. Here it's also remote, okay? And it is a very important machine that will put the correct software and will start the experiment and will collect the result. So it's like the control node that is controlling everything of the experiment. Now, the Sophia node itself, it's all this box that is down. Sophia node is our slices node at Sophia Antipolis. So it has two pieces. One is called data center, and what's called anechoic chamber. So the anechoic chamber contains the radio, and the data center contains servers that can run software. So the G-Node B, which is the base station, will be launched on one machine on the data center. And the UE, user equipment, the telephone, will also be launched on one machine in the data center. These machines are connected with fibers to the anechoic chamber, where we have USRP N320 and N300 that will run the radio parts for the UE and G-Node B. So when the UE will connect to the G-Node B within the anechoic chamber, and then go to the 5G core to do the ping. So this is the experiment. But when we start, nothing is ready. Nothing is deployed. So here are some configuration aspects. I will not go into the details. So just to show you what is possible to do. So for example, when these are parameters, okay? And then here we can go to the login of the portal.slices. When we log in, so how do we log in? You don't need an account, because you can use your academic account. Okay, so if you type KTH, oh no, it's not KTH, it's ETH. So if you type Zurich, you will go to ETH Zurich, and then you will find that you can connect to this slices now immediately, okay, with your institution account. There's also INRIA, but not only in Europe. You can go to UCLA, for example, and you can see UCLA is available. Okay, let's go to INRIA because we want to run the experiment, and now we can connect. And then now we go to use the experiment that we want, the experiment type, which is Post5G beta. And then we run it. And then here we go into this interface I showed you. And this interface is very important because here we have our deployment node. By the way, we use a system called PAUSE that was defined by Technical University of Munich, and that is integrated in slices that help to deploy the experiment and to reproduce. So here our node, our management node is standard, as you saw in the previous image. And then here we have the resources that we want to book to run some software on top of it. And then here we find that, for example, we can check those two nodes, SOP node F1, SOP node F2, because we want to run the software on top of it. And then after that, we choose our experiment. Here we have the scripts of the experiment. So recall, here we are configuring the infrastructure. And we have infrastructure configuration and experiment scripts. Here are the experiment scripts that we will also integrate in the configuration so that they will be run later on specific machines. Okay, now the core will be deployed because we want the core to be deployed, and we need to put the IP address as we see later, but we will do it later. Yes, here we go there, and we get some IP addresses to configure the core. So here we are running the core somewhere, not locally, and then we add the IP address here. Okay, now we don't have a run. Why we don't have a run? We would like to run ourselves the run. The Gnode B, we want to run it. The UE, we want to run it. So that's why we separate the infrastructure and the experiment. The infrastructure does not involve a run. The experiment brings the run. So here it should be false, not true. And it will be put to false because we don't want the infrastructure to run a core for us. And then we can do the same for UE. For example, here false. FlexRig, we don't have a FlexRig. Why? Because we don't do, sure we have it, true. And then we add some, yes, we have it. We will add the IP address to it because it's needed. Okay, so we put it. And then different parameters of the 5G network. Then what we will do, we start the configuration. So now we launch the configuration. I will not present the whole details. I will go faster in the video because really it's very detailed, step by step what will happen. Okay, and it's very interesting for people who want to launch experiments. But now the goal is just to show you that it works. And here, for example, is a configuration file that was generated. This configuration file contains the whole experiment and the whole IP addresses of the different elements. And this file will go on each node in the experiment, will be deployed by this machine, this control machine, on top of every node in the network, so that it can communicate easily with the same information. A lot of technical details are here about the IP addresses, about the different interfaces that are defined. Okay, just to show you that these are really operational aspects, and they are already running. And then these are very advanced software aspects that can be used and tested and deployed very easily. So you want to do experiment with real 5G, you run it. And your student want to define a new scheduling mechanism, you run this, and then you play with your scheduling mechanism for free, almost free effort. Let's go to maybe faster, 2 times. Here we are. So I don't think that I will go into running the details. But for example, here we have some ping, because if you remember the infrastructure here, you have this machine, the USRP here and there. So what we will do is that we will put this on, we will install the configuration file, then the software, then we will start this, start that. Everything will be started on the fly because we want to deploy ourselves. Maybe for sure we can get some images and avoid to compile. But in this experiment, we do the compilation just to show you that it is possible. Then we are running all these aspects and testing the elements that are running. And then at one level, we will arrive and run the ping. It will show up somewhere, some ping command. Here, everything, Kubernetes was run, the core was run remotely. Everything was done automatically, okay? And then now, so this is MRS. Before MRS. So we have the results. So yes, this is the ping. So here we have the ping that was run, and we have ping with 39 millisecond. 39 millisecond because we run the core in Belgium, in IMEC, in Ghent. They have virtual wall, so they provide access to their resources. We run the 5G core there, and then we did a ping between UE in Sofia, in our anechoic chamber, to go to the core that is in Belgium, and it is like 30 milliseconds. So it's not the radio that provided this huge delay. It is the internet, because we go to the network and then go there and use the regular network for this experiment, okay? And then after that, now we want to store the results somewhere, okay? So what we will do is that we will connect something called MRS. And then we have here the number of the experiment, 332. We go to MRS, and then here is the MRS, and then we will find our results there. So, oh, no, not 5. Okay, so here the experiment is already available. We have 41 meg of data that was stored there, and then we can check the date. We can check many information. So the experiment was done by Damien, and then here are the dates, and then we can download the data and now go and check different information of this data. For example, the configuration file. So we can check that the configuration file that was stored is exactly the same that we used, and we have all these format, tar, zip, etc. to provide the information. And here is what we downloaded concerning our experiment. It will show up in a window, and then we can check that the different files, these are the different files. Here, for example, the output, we can check the output of each node of the experiment. Everything was stored and archived for the use of the researchers if you want to check the conditions. And we have also very wonderful feature, that is the monitoring. We can provide information on the monitoring of the of what happened during the experiment. Here it is, blueprint monitoring. So you can check, for example, here the results. This is what happened during the experiment. On each node, you can check the CPU, the memory, etc. And then you can follow back your experiment. If something didn't go correctly, you can know why. What happens here? Why do I have a peak here? Or why do I have a drop at this level? So these monitoring tools are provided, and the data that was stored about the experiment allow you to come back and to test everything afterwards, not only in real time, but afterwards. Okay, so this is all what I wanted to say about this experiment. Now I run it maybe in fast mode, but no need to be slower than that at this level. Now I go back to the slides to finish. So this is show you that to define all these aspects, we gathered with 5G researchers. We define what is needed. We use the generic hardware to run this software, okay? But the interface allow you to program your infrastructure, then to run your own experiment on this infrastructure. We could have run, for example, the core locally and run the same experiment of ping, and then the ping would have given 10 milliseconds instead of 39, okay? And what is our roadmap up to now? We started this work with Serge and many others in June 2022. So we are like soon to be 3 years, okay? The first proof of concept was 1 year after, first deployment 6 months after, And then we did some deployment with non-slices member, which is people with Amarisoft, for example, that do not have open air interface. And we were able to interoperate with them. We did some hackathons, some code sprints, and then we went into pre-operation in November this year, last year, sorry, 2024. So this is the major date, pre-operation on 11/11/2024, which opened this to any researchers. So anyone from ETH who is interested and could not join this presentation can go to the portal address that I put in the end of the slides, and then can go there and play with what is existing. We did another code sprint, and then we have another hackathon that is expected at the networking conference in June, where we expect to release version 3 of the blueprint. Okay, so what are the lessons learned? I think I need only 5 or 10 minutes maximum. So what are the lessons learned? What we can do up to now is to run the infrastructure on premises. So you can run it at ETH, you can run it at INRIA, you can run it at Euricom, you can run it at University of Thessaly, at Sorbonne, and we can do the core RAN split, and we can also do different versions of the split. We can run the CU in place, DU in another place. So all these are possible. And well packaged. All the configuration tool I showed you allow for all these. So if you run it on premises and you want to connect your functions, well, you can use dedicated fiber like INRIA Euricom. Okay, between INRIA and Euricom we have dedicated fiber. But between INRIA and UTH, we don't have dedicated fiber, so we use either commercial internet or international dedicated VLAN. For example, with IMEC at Belgium, what I showed you, use international dedicated VLAN at 1 gigabit per second with 10 millisecond delay. With UTH, Sorbonne and UTH used commercial internet, so for the connectivity, so you can put at one place part of the deployment, at another place part of the deployment. Even in some cases you can put part of the deployment in a public cloud. For example, when we did experiment with Greece, we found that the delays are so high. So what we did is that we run part of the network in the cloud, okay, Google Cloud. And then we did experiment with INRIA, Google Cloud platform, and University of Thessaly. So it works very well. So this is very nicely complementing each other. You can use specific test beds like the IMEC we did in this specific demo I showed to you, and it operates with another other than operator interface like Amarisoft. Okay, other lessons that I will not get to up to now is that we should really pay attention to aspects that people do not take care of, which is network interconnection, authentication, etc. These are very important aspects, and we should ensure to provide VMs, because people want to test at the beginning in VMs, then go to the real network. And this word means that people can avoid the reservation system when they know that you do not enforce the reservation, and then it's only you indicate that it's reserved and go directly to use the resources. So we should really take care of protecting the resources, but it is not done. It's being done now. So we added something to provide this separation. Okay, so this is the list of equipment that is offered at Slice's site. Really, it is very, very advanced radio, like these RUs that are compatible with Oran, Benetel. We have Lighton with frequencies like on the band 78, and we have FR2 on the 26 gigahertz. We also have AW2S. So all these radio units are available at Sofia, either Eurocom or INRIA. We have multiple UEs at all sites, okay? Quectel UEs, and we have real smartphones that can be used. We have programmable radios to run the radio part, okay? Like a USRP. We have these different types of USRP, which are very advanced. We also have Kubernetes clusters that are in different places with large capacity, and we are augmenting this because many people are putting things. We are adding, we will add, and the others will add. So these can help to, for example, we run the core in one remote Kubernetes cluster. We also have on different places local compute resources if you want to run some compute function near your RAN and you don't want to run it on a remote place. We give access to bare metal to last generation servers, Intel and AMD, that are really performance oriented, and one of the servers costs 20,000 euros or more even. So just to show that these are, you can go there and get access to it and run what you want, okay, on top of it. And most sites offer synchronization with PTP. So we have GNSS-based synchronization, okay? And the good news, recently, we are able to provide in April, we will be able to provide in April half a petabyte of storage, 500 terabyte of storage to store the information from the experiments. Okay, so this is an image showing the INRIA data center, the anechoic chamber, and Eurocom with the fiber here, the Sofia node, and here is more detailed map of the equipment. We have all the details of the hardware here. This is Eurocom. This is INRIA anechoic chamber. This is INRIA data center. In fact, it is called INRIA data center, but Eurocom also puts some equipment here because we are doing things together, okay? So here we can have machine for compute, bare metal machine that can be used to run your functions, front hall specific to telecommunication, and this we can connect to Greece, to Italy, CNR, to Sorbonne, to Spain, etc., to TUM in Germany. And these are the storage I was talking about that will come in March, in fact, not in April. In April, we will add some GPU machines, sorry. Okay, so this is the last group of slides, 3 slides. The last features that we are adding is a generalized meta model for the resource description that was very helpful to do the learning for LLM, for a large language model, okay? So that we have a chatbot to help deploying your experiment, okay? So I can show you here, for example, if you go to the interface, you have a chatbot and you ask, hello, he will ask you, how can I assist you today? I want to add a new UE to my blueprint. Which values should I change? And then we have, I don't scroll everything here, but you have like 2 or 3 pages of information provided by the chatbot that was trained by the detailed information about the blueprint. This is one of the aspects that is very interesting. We can have a helper. We don't have yet the paper writer helper that will write your paper after the experiment will run. Here is another use of the chatbot, which is, I want to change the parameter of the UE. Which parameter should I change? So it will explain to you all the details. So this is one, we have one entry point for everything. You go to this page, doc.slices.ri, and then you go here, and then you will go to the request a slice account. And if you have an account, which is the case for you, you can go directly, and then everything is explained. We have here Blueprint services. The good news is that we don't only have the Post5G Blueprint that I showed to you. There is a blueprint for federated learning. So if people want to use federated learning experiments, they can use this blueprint. And we have basic infrastructure, S3 storage, machine learning, connectivity, other that will come later. Okay, so this blueprint approach can help to use the same infrastructure, the same nodes, but to provide different customized infrastructure for the user to run their own experiment. So that's all what I wanted to say. And if you have any question, you can ask Damien or myself or Serge Dida at Sorbonne University. And thank you very much.